Number 1. So this is a static equilibrium problem. So we're going to draw the seesaw. And we have one boy over here, so his weight is going to exert a force downward here. And we have a girl here. And we don't know where they are, but it doesn't matter. We can just say that this is R1 and this distance is R2. And this force here is F1 and this one is F2. So for all static equilibrium problems, you should sum up the torques, set them equal to 0. So the F2 is going to cause the object to rotate clockwise. So it's going to be a negative torque. So minus F2 R2. And then F1 is going to cause it to rotate counterclockwise, positive torque, plus F1 R1 equals 0. So whenever you just have two forces that are on either side of your pivot point, then it turns out that those two torques are going to be equal to each other. You're going to have F1 R1 equals to F2 R2. So from now on, when we have this case again, I'll just set up the torques equal to each other to save a couple steps. So this question is asking, well, what happens if they move into half of their original distance? Well, that just means that you would have R1 here divided by 2 and R2 divided by 2. And you can see that this doesn't change the equation at all. So if they both move in by the same fraction of their distance, so if they both moved into a third of their distance, it would still be balanced as well because the two sides still remain equal. If you divide one by 3, you divide the other one by 3, the torques will always balance. Number 2, so a meter stick is balancing at the 50 centimeter mark. So what that is telling us is that this is a uniform stick. And now it says if a mass is placed at the 90 centimeter mark, then it's going to balance at the 61 centimeter mark. So what's the mass of the meter stick? So just to visualize what's happening here, so normally the stick would balance like this. You'd have a string here, and the weight of this side of the meter stick balances the weight on this side, so it's perfectly uniform. Now what's happening is that we're putting a mass over here, a force here, and now the stick will balance here at the 61 centimeter mark, right? This is simply because now that you have extra weight here, you need to reduce the torque provided by this side by reducing the distance and moving that pivot point over to the right here. So let's set up this problem. This is a static equilibrium problem. We know that the stick is perfectly uniform from this diagram, so we can say that the weight of the stick acts right here at the center. So this is going to be F1 and R1 here, and the 50 gram mass will cause a weight here, F2 and R2. So like the previous problem, the torques are going to balance. So we know that F1 times R1 will equal F2 times R2. Now what we need to do is plug in different values here. So let's define them. R1 is going to be 11.3 centimeters because this is at the 50 centimeter mark and the pivot point is at the 61.3 centimeter mark. And then R2, since this is at the 90 centimeter mark, 90 minus 61.3 is going to give us 28.7 centimeters. And then F1 is going to be the weight of the meter stick, so I'll call it mg. where m will be the mass of the meter stick, that's what we're looking for, and F2 is going to be the weight of the 50-gram mass, so I'll say 50. Actually, I'll convert it to well, actually, we don't need to convert it to kilograms because the answer is in grams. So if we leave everything in grams, then the units will cancel out. So I'll do 50 times G. So now when we plug these in here, then we're going to have mg times R1 equals 50G times R2, so the G's will cancel out. And since this mass here is in grams, that means that this mass here will be in grams. Likewise with the distances, since they're both in centimeters, we can leave them in centimeters. So the mass is going to be 50 times R2 divided by R1. Plug in these distances here, the units cancel out, and we'll get 127 grams.